Yeah.
Thank you, Professor Clark, for a fascinating talk. As a review of the history of thermal oxide, but also point out the new directions that we should be looking at. Now I'd like to open the floor for questions. So one thing you mentioned in this zinc oxide, you touched on zinc oxide and the indium oxide system. Somewhere in the middle, there's a mixture of different kind of, it's a mixture of phonon modes as well. Of course, phonon can be very important for optimizing the properties of thermoelectric materials. How do you use the Raman measurements and use that to help you to design these or improve the Z value for your thermoelectric materials?
Well, of course, as what often happens in science, you have the explanation after you have the results. To get low thermal conductivity in a layered structure, you'd like to be able to have evidence for zone folding. So I can say, look, I have low thermal conductivity, but someone else might say, well, what's it due to? So by looking at Raman spectra of very low energies, so this is well under 100 wave numbers, you can actually see new modes appearing that happen to be that are periodic. You can calculate, you can measure the energy, and you can relate this to the band structure. So the image I showed you actually had the band structure of the zinc oxide, but not knowing all your backgrounds, I left that out. But the bands that we see in the low energy Raman correspond to the zone foldings that we would expect from the phonon spectrum.
So that's a nice talk. One of the questions I have, I don't think I need anyway. Okay, so regarding the indium oxide, zinc oxide superlattices, in fact, you can reduce the thermal conductivity quite a lot.
Yes.
But then, as you know, the ZT also depends on the electrical conductivity.
Yes. Mm-hmm.
So those standard conventional material like bismuth telluride, all those things, they almost behave like metal. The conductivity is like metallic conductivity, basically. Yeah. But when you talk about oxides, it's a really long way to go to enhance because they're wide band gap, and even if you dope, it's not that going to have a high electrical conductivity. So what do you think about this one?
Well, I think it's clear to get the electron conductivity up, we also have to dope the zinc oxide. And that's why that last bullet I had said that if we add aluminum, for instance, you can dope the zinc oxide. So that's an area you have to pursue in order to get the electron conductivity up.
So one of the thing is, doping, of course, it enhances.
Yeah.
In fact, we work on zinc antimony-based material. So when you dope it, of course, the the concentration of carriers enhanced.
Yes.
And then the thermal conductivity goes down as well. Thermal conductivity goes up because when you transfer the electrons, that's the equation we see that there's one parameter, the phonons assisted with the transport of electrons. So this is really hard to play around with the kind of calculation. So regarding oxides, because there are a lot of papers, because oxide has been used as a semiconductor for decades, but I don't see anywhere that they can dramatically enhance the electrical conductivity, like if you talk about bismuth telluride or other structures.
Yes, I'm not sure that people have actually used zinc oxide as a semiconductor very extensively, but we know how to dope the material. We don't know what the optimum doping in zinc oxide is. Antimony is one, it's 5+ ions, so it goes in. But the advantage of being able to dope the grains separately from the interface between the zinc oxide and the indium oxide, I think gives us added degree of freedom that you don't have. Certainly, as soon as you add anything to zinc oxide, in pure material, you drop the thermal conductivity. You can't drop it as much as having these layers. So not pretending that we've optimized this in any way, but this is an alternative approach. But I want to hear how you do with your antimonite.
Thank you. Thank you for an interesting talk. You've clearly made the point that high temperatures are valuable, but a lot of the heat around us in the environment is not at that high temperatures.
Yes.
And so does that leave space for other materials that are operating at lower temperatures?
Oh, yes. Yeah.
And I'm thinking, for example, even of organic thermoelectrics. Are they still viable, and do you think there's future for them?
There are certainly reports of organic materials that are thermoelectric. They don't have very high ZT, but there are particular polymers that have thermoelectric properties. I think it's too early to tell. It's one of these things where the polymers are sort of catching up. Whether they will ever be as good as bismuth telluride or one of these compounds, I personally don't know. But, yes?
One recently Japanese company, they made a thermoelectric watch. So they made up of polymer. In fact, they use the body temperature and the temperature of your body and the ambient and the atmosphere. So of course, the efficiency is not very high, in fact, but you create very low power, but it can run a digital watch. So this is the latest information about the Japanese did that.
Well, that's more of a testament to the ingenuity of the electronic engineers who can now make circuits that don't require very much power, that you can use very little power to power them. And that's why I actually had it as separate. You know, if a mechanical watch doesn't require any power once you're wound it either.
Thank you very much for this very nice talk. I'm sorry for my voice, but I have some important question to ask. So, how about twin boundary for this so-called low temperature material? So, is it twin boundary is better? This is the first question. The second question: if we are able to produce nanocrystal combined with amorphous structure, so some sort of a nanoglass. Is it an interesting structure for the high temperature, not for high temperature, for the electric power generation?
So let me answer those two questions in turn. Twins will certainly affect phonon transport, but they're not very effective because you'd ideally like to have a mismatch in, say, the atomic mass or the atomic arrangement. So twins, I don't think...
I talk about the stability compared to the nanogram boundary. Nano twin boundary is more stable for the same composition.
I don't think very much has been done on nanotwin materials and the thermal stability. It's difficult to believe that it'll be very stable at high temperatures because generally if they're transformation twins, they don't require very much energy to move them. That's why you can get a lot of them in the nanotwins. The composite materials is very interesting because Israeli scientists some 20 years ago did an analysis of two-phase thermoelectrics. And you can't get a higher ZT than the higher of the two phases.
Okay.
But you might be able to get some interesting temperature dependence that that nobody's explored. And in fact, there are some thermoelectrics that are very quenched, and there are some amorphous phases, but they tend to be very thin phases rather than a true composite. Okay. So it's another area that should be explored.
Okay, thank you.
So maybe a related question. You mentioned nanostructured materials. It seems to me it's a double-edged sword. On one hand, nanomaterials will give you a much enhanced phonon scattering, therefore dramatically reduce the conductivity. On the other hand, you have interfaces that also drops the conductivity. And thirdly is at high temperature diffusion can become a problem. I mean, then the material becomes unstable. Do you have any comments on how to optimize the this nanomaterial structure, or how?
Yeah. these natural superlattice structures.
Okay, so
Optimized Seriously, they might not have the electron density we yet need, but the structure is dictated by the composition.
So you are using chemistry to tune the structure.
Yes, yes, yes. I hate to say it, but yes.
Last question. Oh, the students, yes.
Very quick question. I just want to know what is the bonding between the zinc oxide and the indium oxide?
I'm sorry, what's
The bonding. The force.
Well, we tend to think of it as being ionic bonding, but there's invariably some covalent bonding. But exactly what proportion there is in these compounds, I don't think we really know. So the reason we like to build these structures with on the assumption of ionic bonding is then you can use Pauling's rules and you can do lattice sums and all the rest of it. But it doesn't mean, say, it's truly ionic bonding. It can't be purely ionic bonding because it wouldn't have any conductivity. So, questions from the back?
Students? Okay, if not, I'd like to thank Professor Clark one more time for his wonderful talk. And at